Hello everyone, welcome back our class BNC 31803. We are still in chapter 4 and today we will continue our class on part excavation retaining systems in soft soils. Let go. Retaining walls are structures designed to restrain soil to unnatural slopes. They are used to bound soils between two different elevations, often in areas of terrain possessing undesirable slopes or in areas where the landscape needs to be shaped severely. The criteria for the selection of type of wall are size of excavation, ground conditions, groundwater level, vertical and horizontal displacements of adjacent ground and limitations of various structures, availability of construction, cost, speed of work and others. The common making up a retaining structure can be broadly classified into facings and supports. Types of earth-retained walls are 1. Braced walls, soldier pile and lagging walls. 2. Sheet piling or sheet pile walls. 3. Pile walls, contiguous, secant. 4. Diaphragm walls or slurry trench walls. 5. Prefabricated diaphragm walls. 6. Reinforced concrete, cast in situ or prefabricated, retaining walls. 7. Soil nail walls. 8. Coffer dams. 9. Caissons. 10. Jet grout and deep mixed walls. 11. Top-down construction. 12. Partial excavation or island method. Retaining systems for deep excavation, common system. 1. Contiguous piles. In this technique, the reinforced concrete unconnected piles are installed in the periphery of the proposed site. The contiguous piles wall is designed in such a way that it resists the lateral earth pressure of retained soil. The width of gap between piles varies between 50 and 500 mm according to ground conditions. The diameter of these piles varies from 300 to 1,200 mm normally. The soil between two piles is stabilized by shotcreting. Shotcrete is mortar or high-performance concrete conveyed through a hose and pneumatically projected at high velocity onto a backing surface. It is the force of this spraying action that leads to compaction of the concrete or mortar, which then forms layers of concrete to the required thickness. Typical depth of excavation supported by this system is 5 to 10 meters without tie-back anchors. 2. Secant piles. In this technique, primary piles, PCC, are installed first with secondary piles, RCC, constructed in between primary piles when it gained some strength as shown. Pile overlap is typically in order of 3-inch, 75 mm. 3. Sheet piling. Sheet pile walls are constructed by driving prefabricated sections into the ground by vibration in sandy strata and by pressure in cohesive strata. Following are the typical steps involved. 1. Position of sheet pile. A guide frame or guide beam is placed on the ground to set out the position of the sheet pile wall. 2. Installation of first sheet pile. The piling rig lifts up the first sheet pile and drives it into the ground, leaving about 1 meter length of the sheet pile above the ground level. 3. Installation of second pile. The piling rig drives the second sheet pile into the ground and the second sheet pile interlocks with the first sheet pile. 4. Repetition of process. Process 2 and 3 repeats till the installation of sheet piles is completed within the length of the guide frame or guide beam. 5. Extension of sheet pile. If the first set sheet piles installed are not long enough to reach the required depth in the ground, extension of sheet pile is required. This is done by welding the ends of a second sheet pile length to the one driven in earlier and driving the combined length into the ground. 4. Diaphragm wall. The continuous diaphragm walls, also referred to as slurry wall, is a structure cast in a slurry trench by tremmied concrete. A tremmy is a watertight pipe, usually of about 250 mm inside diameter, 150 to 300 mm, with a conical hopper at its upper end above the water level. It may have a loose plug or a valve at the bottom end. Then, the trench is initially supported by bentonite polymer-based slurries. The construction sequence is illustrated in Figure 17. The construction sequence of diaphragm wall are: A. Trenching under slurry. B. End stop inserted, steel tube or other. C. Reinforcement cage lowered into the slurry-filled trench. D. Concreting by trummy pipes. 5. Vertical soldiers and horizontal lagging king post method. The method consists of boring holes on the wall line, typically at 2 to 3 meters centers, placing vertical steel universal beam or column soldier piles within the holes and concreting the base of each joist below final formation level. Lean mix concrete is often used for this purpose. In suitable soils, the steel soldier pile may be driven. When the soldier pile is to be extracted, the base of each joist is supported by gravel backfilled to formation level. As bulk excavation proceeds, horizontal lagging timbers or precast concrete units are wedged between the soldier piles. Steel section wallings are placed to take the thrust from the soldier piles to ground anchors drilled at intervals along the length of the wailing beam. Wailing is a type of support structure used in excavations. Alternatively, each soldier pile is anchored and a wailing is not needed. Let's see some case studies on real situation. Case Studies 1. IT Tower, Lahore. Situation: IT Tower is a 24-story high-rise building, have 18 superstories and 6 basements. It is located in Gulberg 3, Lahore, surrounded by roads on 2 adjacent sides and residential buildings on other 2 sides. A stratum consisting of clay and silty clay is present from 0 to 8 meters depth in silty sand/poorly graded sand with silt subsequently. As the groundwater table in the city is at a depth more than 100 feet, therefore, water was apparently not a problem. What we need to do for substructure work on this project: shoring piles of 2 feet diameter and 3.5 feet center-to-center spacing was designed. 5 layers of anchors as per design were to be constructed. Anchoring angle was 15 degrees and length of the anchors varied from 25 to 57 feet. Depth of the piles was 97 feet and proposed depth of excavation was 65 feet. A tie beam of depth 1.5 feet and width 2 feet was provided as shown in Figure 18. Case Studies 2. Alamgir Tower, Lahore. Situation: Alamgir Tower is a high-rise building of 42 stories. The site is surrounded by a 10-story building on one side, 3 stories building on the other side, a road in front and a residential building in the rear. Proposed excavation depth is 85 feet. A stratum consisting of clay and silty clay is present from 0 to 8 meters depth in silty sand/poorly graded sand with silt subsequently. The groundwater table was below 100 feet. What the best solution to proceed the substructure work? Contiguous piling with anchors and tie beam was adopted as the soil retaining system. The depth of the piles constructed was more than 96 feet. Anchoring at an angle of 15 degrees was to be done in 9 layers as shown in Figure 19. Case Studies 3. Washington Convention Center, Washington, D.C. Situation: the project is at the present time the largest single-basement slurry wall excavation in the United States. The excavation site is approximately 1,480 feet long by 500 feet wide. At the north, the excavation is 55 feet deep along North Street, but only 30 feet deep along the southern side. So, what the best solution to proceed the substructure work? Slurry wall panels adjacent to the subway at 7th Street are 3.5 feet thick, while at all other locations the wall thickness is 3.0 feet. The slurry walls also provide water cutoff and thus minimize the dewatering efforts that are required. Temporary bracing for this excavation consists of a mix of tiebacks and pre-stressed breakers, depending on location. The largest slurry wall deflection, 0.7 inch, occurred at the deepest section of the excavation along North Street, where the wall was braced by 3 levels of tiebacks. This deflection was not measured directly, but it was reconstructed from data before and after reinitialization of inclinometers took place. The wall slightly bent only below the lowest tieback level, and above that showed very little to no bending. Cantilever movements dominated until the second tieback level was installed. The largest horizontal soil movement, 0.75 inch, occurred at the southern side where the excavation was only 30 feet deep, braced by an upper level of tiebacks and a lower level of rakers. Type of wall support are 1. Soldier beam and lagging. Pairs of soldier beams are driven to a depth slightly below the final excavation. Their spacing is in the order of 6 to 10 feet so that available timber can be used for lagging. The lagging timber, which is slightly shorter than the spacing but on the order of 2 to 4 inch thick, are installed behind the front flange to retain the soil as excavation proceeds. Some hand excavation is usually required to get the lagging into the place as per shown in Figure 20. Soldier piles are installed with conventional pile driving equipment or in augured holes. The horizontal sheeting or lagging is installed behind the flange closest to the excavation, inside flange. The sheeting can be installed on the inside face of the front flange and held in place by various methods such as clips, welded studs, or bars, etc. The soldier pile and lagging method is inappropriate for perfectly cohesionless soil. For cohesionless soils, sheeting must be used. Figure 21 showed the workers install lagging, while Figure 22 showed the soldier beam and lagging retaining wall. 2. Soldier pile, tremi-concrete, SPTC. SPTC is used for very difficult conditions in soft ground with a high water table. Soldier piles are set in pre-drilled holes, and the space between flanges of adjacent soldier piles is excavated and filled with bentonite slurry. Reinforcement is lowered into the trenches and tremi-concrete is placed. As tremi-concrete displaces the slurry, it is collected and recycled for future use. The final product is a continuous concrete wall beneath the ground surface prior to excavation. After completion of the wall, excavation and interior bracing can begin. Figure 23 showed typical free-hanging mechanical clamshell for slurry trench excavation. 3. Soil nailing. Soil nailing is an in situ reinforcing of the soil while it is excavated from the top down. An array of soil nails which are passive inclusions are installed in a grid that functions to create a stable mass of soil. This mass of reinforced soil functions to retain the less stable material behind it. In the right soil conditions, soil nailing is a rapid and economical means of constructing excavation support systems and retaining walls. In many applications, soil nailing can be the least disruptive way to construct a retaining wall. Soil nailing requires an unusual amount of handwork, craftsmanship and geotechnical knowledge to construct. The typical construction sequence begins with the excavation of a shallow cut. Then shotcrete is applied to the face of the cut and soil nails are drilled and grouted. This sequence is then repeated until subgrade is reached. Example on soil nailing. Northwest Animal Facility, University of California at Berkeley. Construction of an underground laboratory at the UC Berkeley required temporary shoring on all 4 sides of the excavation. The tolerances for the shoring was specified to be no more than plus or minus 1 inch. The excavation depth varied from 15 to 37 feet, and was constructed in colluvial soils, consisting of stiff sandy clays and dense clayey sands with gravel and some cobbles. Approximately 14,000 square feet of area was soil nailed. Another example on soil nailing. Chemistry Building, Washington State University, Pullman, Washington. The 40 feet deep excavation at this site was made in stiff to hard, slightly clayey silt, with standard penetration resistances ranging from 15 to 45. The silt had a cohesion of 200 psf and a friction angle of 28 degrees. At one corner of the site, A two-story brick auditorium was located 10 feet behind the soil-nailed wall. The movement was less than 0.3 inches at the face of the wall, less than 0.2 inches at 18 feet behind the wall, and less than 0.1 inches at 36 feet behind the wall. 8 rows of soil nails were designed to support the excavation, and another example on soil nailing. The Beckman Center, University of California, San Diego. Construction of the new chemical science building at the Scripps Research Institute required an excavation of up to 57 feet deep. The job consisted of 75% soil nailing and shotcrete and 25% of soldier beam and tieback shoring, and a total of 24,080 square feet. The soldier beams and tiebacks were utilized where soil nails would have interfered with existing buildings and new or existing utilities. The deepest section was shored with 10 lifts of permanent soil nails. As per shown in picture above. A permanent shotcrete facing was installed in front of the shoring system, which was completed in 10 weeks. 4. Excavation bracing. For narrow excavations, internal struts are most appropriate. Before struts are installed, a horizontal member called whaler is placed against the soil support as per showed in Figure 24. Intermediate struts are then installed from whaler to whaler across the excavation. Crosslot struts are not feasible for very wide excavations. For very wide excavations, raker bracing is used. The support for the rakers, driven piles or footings, are installed at the bottom of the excavation. Construction of the soil support and removal of the remainder of the excavation then begins. Compared to crosslot bracing, in raker bracing system the central portion of the work area is relatively uncluttered as per showed in Figure 25 and 26. 5. Tieback systems. Tiebacks, or anchors, are structural system which acts in tension and receives its support in earth or rock. The system consists of the earth or rock, which provides the ultimate support for the system. A tension member, or tendon, which transfers the load from the soil retention system to the earth or rock. A stressing unit which engages the tendon, permits the tendon to be stressed, and allows the load to be maintained in the tendon. Earth anchors are usually installed at an angle of 10 to 20 degrees down from horizontal as per showed in Figure 27. If the acceptable soil is not encountered at these levels, it is necessary to change the angle to engage the proper soil stratum. Anchors or tiebacks eliminate obstructions in the excavation inherent in rakers or struts. They consist of rods that extend well beyond any potential failure surface into firm undisturbed soil or rock. Some tiebacks are made with high tensile cables grouted into rock and pre-stressed against a wale, and others utilizing ordinary steel rod or reinforcing steel. Figure 28 showed tieback concrete wall constructed underground for excavation support. Tieback systems are generally very successful in preventing movements of the excavation walls. Usually, the excavation wall is left in place after the permanent construction inside the braced excavation is complete. It is often used as the back form for the permanent basement of the structure. Tiebacks, if left in place, are always cut to relieve tension when the permanent structure can safely carry the load. Figure 39 showed tieback being installed, example on tieback systems. 2 Renaissance Square, Phoenix, Arizona. This is a 63-foot deep tieback excavation. The subsurface material through which this major excavation was installed consisted of 25 feet of medium dense to dense sands and gravel, underlain by very dense sand, gravel and cobbles, SGC. The SGC contained a large percentage of cobbles up to 18 inches in diameter. The job consisted of 62,000 square feet of shoring and 500 tiebacks, properties of commonly used excavation support systems as per showed in table below. The table also explained the advantages and disadvantages of the system for 1. Diaphragm or call slurry wall. 2. Sheet pile wall. 3. Soldier and lagging wall. 4. secant wall or call tangent pile wall. 5. Micropile wall, modes of failure for excavation support systems. Figure 28 showed common types of failures in supported excavations. A. Overturning. B. Sliding. C. Overt stress of foundations. D. Overt stress of the wall. E. General stability. F. Berm and simple slope failure. G. Bottom heave. H. Buckled excavations. 5 steps of excavation are: 1. Rough staking. This process is necessary to identify approximately where a home or other building will be situated. If trees or other obstacles will have to be moved, rough staking will make this more obvious by placing stakes around the designated area of where the structure will be built. 2. Clearing. If your excavation site has vegetation or tree roots that have to be removed, this happens during the clearing phase. If there's a significant amount of this material, you may need to decide where all the debris has to be hauled to. 3. Excavation. Any building that requires a basement will have to be excavated, and the dirt which is removed will have to go somewhere. You can count on heavy equipment like a bulldozer or backhoe to be involved in this phase, as well as dump trucks to haul away fill. 4. Rough grading. Some of the dirt which was removed during excavation can be backfilled around the home to establish the right pitch toward the curb, for drainage purposes. Then you'll also have to overlay that fill dirt with the richer topsoil that was removed, so that grass and shrubbery can grow well around the home. 5. Erosion control. Some locations have regulations about not allowing topsoil to be eroded away by runoff from heavy rains, so you may have to investigate local restrictions on this. In any case though, steps will have to be taken to prevent your cleared plot of land from having soil washed away and possibly into adjacent properties. This ceases to be an issue once grass is growing on the land, but until that happens, the effects of erosion must be accounted for. Okay, that's all for today. Thank you for your attention. See you the next class. Bye and take care.